For as long as we know, people have always wanted to keep secrets, and have spent a lot of time and effort coming up with ways of accomplishing this. One of the most famous examples dates back to Caesar's own cipher. Back then, Caesar and his officials would meet in private and exchange a number by which they would shift the letters in the messages, so that if anyone else picked them up, they wouldn't be able to decipher the message. As time moved on, the ciphers became much more complex, but every cipher had one thing in common. To establish the rules for encryption and decryption, the participators had to meet in private first. In 1976, Whitfield, Diffie, and Martin Hellman published a paper that fixed this problem, thus creating public key cryptography. They described a way, using open channels, to exchange a secret key by the use of the one-way function, the discrete logarithm. Diffie and Hellman opened the door to a new era in cryptography, through which emerged the RSA crypto system in 1977, El-Gamal in 1984, and much more. Let's look at an example that doesn't involve math first, so that we get an idea of what's going on here. This demonstration will be using colors, and our one-way function is mixing, since it's easy to mix colors, but telling someone exactly what colors were used to achieve the mixed color is rather difficult. Let me introduce our trio of people. Alice and Bob are our two communicators, and Eve is the eavesdropper. Let's say that Bob wants to establish a secret color with Alice, but he knows that Eve is always listening to everything that he and Alice say. So how is Bob going to do this? First, Bob chooses a public color, yellow, for him and Alice to share. Next, Bob chooses a private color, blue, and mixes it with the yellow. The resulting mixed color, green, becomes Bob's public color, which he now sends along with the yellow to Alice. Along the way, these two colors are intercepted by Eve. Now that Alice has the yellow and the blue, she also picks a private color, pink, and mixes it with the yellow. She sends the resulting mixed color, orange, to Bob, and along the way Eve intercepts this color as well. But what do they do now? How do they produce a secret color out of the colors they have in front of them? Well, what if Bob mixes blue and orange together, and Alice mixes pink and green together? Now Alice and Bob have established the secret color, dark green, since dark green is pink mixed with yellow and blue, and dark green is also orange mixed with yellow and pink. Also, there is no way for Eve to figure this color out, since she only has the colors yellow, orange, and green. So what does this all have to do with math? We'll revisit our color example, but instead of mixing colors, we'll be using modular exponentiation as our one-way function. First, Alice and Bob agree on a prime modulus n, and an integer g of large order, mod n. Then Bob picks a private integer b and forms his public key, capital B, by raising g to the bth power, mod n. He then sends his public key to Alice, and Eve intercepts this along the way. Now Alice picks a private integer a and forms her public key, capital A, by raising g to the ath power, mod n, and sends this to Bob. Eve intercepts this number also, so that she now has g in capital A and capital B. So how do Alice and Bob make a secret number this time? They each take the other's public key and raise it to their private power, mod n. Now Alice and Bob have a secret key, k. Since k equals a raised to the bth power, mod n, and k also equals capital B raised to the ath power, mod n. Also, there is no efficient way for Eve to figure out k by only knowing g in capital A and capital B. This is because this involves what's known as the discrete logarithm problem. If this was normal exponentiation, then Eve would have no problem undoing what Alice and Bob did. But doing everything modulo a prime makes it extremely difficult. There is no known efficient algorithm for figuring out what g was raised to in order to get capital A or capital B when we work mod a prime n. And that's it. Alice and Bob have established a secret key right under Eve's nose. What should they do with this key? Well, that is up to them. They could use this in Caesar's cipher, the El-Gamal crypto system, or come up with their own crypto system. The choice is theirs.